Good evening, participants. I welcome you all for the third day of online AICTE Training and Learning Academy Faculty Development Program on Sustainable Urban Growth, the intersection of smart cities and mobilities. So today we have two foreign resource persons, one from Google and another from Walmart. So the first session will be handled by Jayakrishnan Vijayaraghavan. Let us invite him with a small introduction. Jayakrishnan Vijayaraghavan is a data scientist at Google, specializing in the trust and safety of AI models. With a rich career spanning roles at Twitter, Walmart, and ESRI, he brings extensive expertise in experimentation, causal inference, and machine learning problem framing. Jayakrishnan is the author of 2 books on geospatial data science and has designed impactful frameworks for tackling problems in AI safety, mission information, sustainable, and transportation. He is an alumnus of Anna University, CEG campus, and is deeply committed to empowering others to harness data science for solving real-world problems. Jayakrishnan's work reflects his global perspective, rooted in his experiences across diverse geographies and industries. When he's not driving innovation in AI, he is dedicated to advancing sustainable urban growth and mobility solutions. With a small introduction, I would like to invite Jayakrishnan to proceed with the first session. Welcome you, sir.
Thank you so much, Professor Lavanya, for the kind introduction. Good evening, everyone. And I know it's a bit late for you, and it's a bit early for me. Like it's almost 4:30 in the morning. So I'll not keep it very heavy. I don't have a very heavy set of slides. I have a bit fun topic to discuss. So today I will be covering. Am I sharing my screen?
Yeah, sir, it's visible. You can proceed.
Thank you. Hi. So once again, I'll introduce myself very briefly. Jayakrishnan, you can call me JK. So right now, I work as a data scientist at Google. So mostly on trust and safety systems. But I started off as a what you can call as a geospatial science or GIS. Some of you might have heard of it. Like, I don't know if everyone knows what GIS is. So I'll use a small introductory video to explain my journey before we go into the actual topic at hand, which is ML problem framing. Give me a second. Since my background is in GIS, I will narrate my story also using a map. So is it like audible? Is the sound audible, Lavanya?
Yes, sir.
Yeah, thank you. I began my journey in Chennai, where I proudly graduated from the College of Engineering in the Anna University with a degree in geoinformatics. It was a field that fascinated me, and because it combines the power of data, technology, and geography to solve complex problems. Little did I know that this would be the start of a lifelong adventure across domains, industries, and geographies. After graduating, I started my career at ESRI in New Delhi. If you're familiar with the geospatial world, you've probably heard of ArcGIS, their flagship software. My time at ESRI was brief, but it was impactful. It introduced me to the broader applications of geospatial technology and laid the foundation for my technical skills. Soon after, I moved to Singapore to work on an exciting national initiative called OneMap. This was where I got my first taste of web APIs, mapping APIs, and web maps. It was a thrilling time. I was learning new technologies and contributing to a project that had a real impact on how people accessed geospatial data. However, my stint in Singapore was short-lived as another opportunity came knocking. My next stop was the United States, where I landed in Fort Collins, Colorado. Here, I immersed myself in utility GIS, focusing on power networks and later expanding to transportation networks. This phase of my career introduced me to the world of sustainability and energy challenges, especially in transportation. It was during this time that I developed a solution to a critical problem in transportation graph networks, which earned me a patent. This work shaped my understanding of how data science could address real world sustainability issues. From there, my career took me to various companies, eventually leading to Twitter in early 2020s. At Twitter, or X as it's now known, I had the chance to work with some largest data sets imaginable, solving problems at a global scale. It was here that I honed my skills in causal inference, experimentation, and trust systems. Today, I'm at Google working on AI safety and trust. My focus is ensuring that Google's AI models are trustworthy, reliable, and ethical. Whether it's about delivering accurate responses or safeguarding user data, my role is all about ensuring that users can trust the technology that they're interacting with. It's a fascinating challenge and brings together everything I've learned throughout my career. This map of my life tells a story of growth and evolution, starting with geospatial systems and leading to AI, trust, and safety. Each stop on the map is more than just a place. It's a chapter in my journey of learning, innovation, and impact.
So thank you for listening to that. So I just wanted to share my journey to illustrate, to tie it back to the today's topic, which is ML problem framing. I'm also like a great believer in the democratization of data and data science. So the purpose of sharing my journey was to show that like I come from a very different background than what I'm working right now. So when I graduated, I had no idea about what data science is or machine learning is. But right now, that's my bread and butter. That's what I work day in and day out. So two things like I wanted to call out was like there was a point in time where I was like widely using data science. I was not a data science at one point completely, but I was like kind of a part-time data scientist. I was what you can call as a geospatial data scientist. So I was using data science a lot in my day-to-day geospatial problems. So if there are anyone who is like not aware of geospatial, what geospatial means, it's anything that to do with location-based data, or anything like to do with satellite imagery, transportation networks. So all kind of these location data, any data, any analysis that you do on location-based data or map-based data, that's what you call as geospatial data, right? And that's what my undergrad background was. So there was a point where I was working in this wonderful intersection of geospatial data science. And that's when I transitioned to like kind of pure data science. But what I observed was there is a lot more that data science can offer to like many other fields, domains, not just like geospatial, not just experimentation, like in all domains of engineering, mechanical engineering, civil engineering, sustainability problems. There are a bunch of sustainability problems that I solved using data science techniques. So all I want to, like, if there's one thing that you take away from this presentation, today's session, it's that like data science is really like is like a universal technology. It's just a tool set. Like if you think about it, machine learning, deep learning, these are all just tools that you can use in your own domain. And like, but like we still need to be careful about using it the right way. And this session, I hope, will be a step towards that, how framing problems in a way that's suitable for machine learning. That's what today's talk is going to be. And the takeaway that I want you to have from this session is that like there are many problems that can be solved using machine learning and deep learning. and some can't be. Like, and so this talk is hopefully introduce you to identify which problems can be solved by machine learning and which can't be. And if you, when you identify when something can be solved by machine learning, how to approach it. So that's the overall thing that I'm trying to convey from this session. And like, I'm open to questions at the end. There's not too much in the slides here, so like I hope it to be conversational. So before getting into like the nuances of ML problem framing, I'd like to just introduce the different hierarchies of ML models, or a different, generally what we can call as learning models, like not machine learning models. Just when I call it all these as learning models or universal learning models. So at the bottom of the hierarchy, I would say is still the rule-based engines. So rule-based engines are basically like when you think of all the mathematical and physical formulas that you have, engineering formulas that you have, you know, like if you have an input, you can transform the input into an output, right? So like it's very well defined. Like if y is your output here, like the like a quantity that you're trying to determine, and x and z are the input variables, you exactly know the formula. Like in engineering, you exactly know the formula that you need to derive y, right? So think of y as any quantity, like let's say atmospheric pressure, and x can be something like volume. I'm just making stuff up, but like quantities like this have a very defined formula. So if you know x and y, you know how to transform x and z, you know how to transform it to y. So that's a rule base. So this is known as a rule. This function of x and z transforming into y is known as a rule-based engine, and that's known as a deterministic problem. Means like you will just have one output for a given input. That's deterministic, right? And you know how to transform. So you just need just the input variable values of these variables x and z, and you can conveniently, and if you know the function, like the physical process that's going on, you can easily convert it to the output that you're interested in. So that's the basis of a rule-based engine, right? But here the thing is, you need to exactly know the transformation, how to convert a particular set of variables into a different output variable that you are interested in. So that's rule-based. That's what we encounter regularly as engineers and in the engineering domain, right? We know what we are looking for. The next stage comes the ML models, where you really don't know how. You kind of know that x and c, these are the input variables that likely impacts y, but you don't know how. Like you don't know the transformation function that transform your input variables to an output, right? So think of this as like anything, this y as anything. Like let's say you'd like to y is the housing price in your neighborhood. You'd like to predict a housing price in your neighborhood. You know that housing price is housing price of a particular house is determined by, let's say, the number of bedrooms, number of bathrooms, presence of lawn, so like different features like this. So those are these features, but you don't know how the number of bedroom will impact the price. Like how does it, like what does how does 3-bedroom convert to price? You don't know that information, but what you have is hopefully lots and lots of historical data. Historically, you have the sale prices of houses in your neighborhood, let's say, and you know the values of these like each parameters of these houses. And when I say parameters, it's things like bedrooms, bathrooms, and all the factors that you think influence house price. So once you have that data, like the input data, which is the factors that you think will influence the output, and the actual output data, which is the sale price of the house, and you provide it to a machine learning model, the model will figure out how does these different inputs transform to the given output. So you need not figure out what the function is. In rule-based engine, like the function is well defined by probably scientists or people working like who have worked. We are standing on the shoulders of giants. But machine learning democratizes the product like that process. You really don't need to know what's the underlying mathematical function which transform X to Z. The ML model will figure that out for you, right? You really don't need to know, like when you're starting with ML, you don't need to know how the intricacies of how the ML figures out this F, but you just need to know that given that I have a good enough data set or a historical data set, and I have a proper label data set, like that's the output data. In the case that I mentioned, the housing prices in your neighborhood, right? If you have historical data about these, all these variables, you can predict the housing house price of any houses that comes to the market in the future, or any house that's there in the even not in the market. Like you can estimate the price of the houses. But the one small problem with these models, there are lots of problems. Like we need to get it right. Like there's a few nuances that we need to take care of. There are a few steps, but the main thing that we need to understand is that it's not deterministic like the rule-based engines. All the models above this level are probabilistic models. And when I say probabilistic models, the simplest explanation for that is, like, for one input, you're not guaranteed to have one output all the time. Like if you vary something in your model, like if you change the model, if you even change the model's randomness, your output may vary a bit. So you're never guaranteed for like one exact output for a given input. So it can vary. And two, sometimes your outputs can have probabilistic values. Let's say I'm predicting that the particular house price is whatever, like I say 10 lakh rupees. So it usually comes with a probability value. Like I don't say with 100% confidence. I usually say, oh, I'm 92% confident that something like I'm 95% confident that the value is between 10.5 to 11.5 lakhs. So the outputs look like this. There is some level of uncertainty that creeps in beyond this level in the hierarchy. So these are two things that you need to be comfortable with before starting to work with ML models or any learning models, right? Like they are probabilistic, and there is some level of uncertainty that comes with the output. And whenever you need a one concrete output, you're probably doing some kind of aggregation. Like there is a range and you're just picking the middlemost value or an average value or something like that. So always keep that in mind when you're dealing with machine learning models. Your output is mostly a probabilistic output. Think of this as like rain forecast. Like someone says that, oh, it's gonna rain tomorrow. That's a predictive model. That's a ML model, which is probably doing the job. When weather forecasters say that it's gonna rain tomorrow, they actually mean what you have to actually infer is, or what the question that you have to ask is, with what probability? What's the probability that it will rain tomorrow? Like, is it like 92% or is it like 60%? Because that matters, right? Because both these scenarios, you can call it as like it will rain tomorrow. Okay, but with what probability is a question that you might have to ask, be comfortable asking when you're hearing some kind of prediction, when you're hearing some kind of predictive models. And there is another aspect I'll cover that at the end of the slide, which is how to evaluate these models. How do you know that your models are doing a good job? So we'll get to that later. Then comes the deep learning models, which fundamentally changed even even having to figure out the input variables. Means like in the previous example, I mentioned about if you want to predict the house prices, let's say, you try to input, figure out how many bedrooms the house has, how many bathrooms the house has, different features, like you try to gather as many features as possible, right? And like you have to do that hard work of collecting the data for all these variables. But deep learning even made that unnecessary. Deep learning even made that unnecessary. It came along and said, hey, you don't even need to provide me the factors. You just provide me an unstructured data. And by unstructured data, what I mean is something like, let's imagine in the case of predicting the house prices. Hey, just upload pictures of the house, right? You don't need to identify how many bedrooms are there, how many bathrooms are there. Just upload one picture of the house, and I will tell you the price of the house. Right? Sounds weird, but like, let's think about it. A human being is good at this. Like a human being who has a wide range of experience in the real estate market. They know a lot about houses. They have like knowledge of like house transactions of home sales. So just by looking at a house, a human being can actually predict the value of a house, right? So deep learning actually caught up to that. Like deep learning models actually understood how to do that, and it's by something known as universal approximation function. So you don't even need to like provide the features or factors, right? It's good. These models are good enough to like understand from the context. It will extract the features itself. Like from a picture of a house, it will extract information like, oh, does the house look new? Does the house look big? All those things. It will try to understand all those things. But the problem is you don't know what's happening in the background. So that's a problem that we are consistently having as you go higher and higher in the hierarchy. You have less information about what the model. I mean, there are ways to know what the models are doing, but it's really difficult. Like especially when it comes to the next stage, which is generative AI, which is just a domain I am working on. We really have little clue into the inner workings of the model. Like what we can control what the model is outputting, but we really don't know why the model output a specific thing with 100% accuracy. So that's something that we have to like deal with. Like that kind of black box nature of these learning models is something that we have to put up. But we have a very good sense of how it is doing it. We don't know like why it is doing it, but we know how it is doing it. And like going above this hierarchy, it's something known as universal approximation function. I've written a blog about it. I'll share it with you if you'd like, about what a universal approximation is, and like how it is determining, how it is able to, how any given mathematical function these models can basically decipher given enough data. So all you need to provide is like enough data. So in the case of housing price, let's say, all you need to provide is lots and lots of historical images of houses and the historical price, sales price associated with that house. So that's all you need to provide. So once you provide that, the model becomes good to like just identify or predict what or basically estimate what the price of a house will be based just by looking at a photograph, right? So that's deep learning models. And then, as you know, as you might have all interacted with some form of the other, like ChatGPT or Gemini or something like that, that then comes the generative AI models, which says like, you don't even need to provide me the data, I will generate the data, right? Like now it can create its own images, it can create its own text, it can summarize anything. I need not like tell you like how to use this. You are already you might already be using it on a large scale. Like this is very much democratized in my view. but the middle two layers are still not too much democratized. So I will be mostly covering about the middle two layers of the hierarchy in this session. Any questions so far? Okay. I'll anyway have time for questions at the end. So, no worries. So this is just a simple demonstration of what the universal approximation is trying to do. I mean, this is a way too easy example. Like it can, these universal learning approximation functions can do much more than fitting a curve. It can fit like multi-dimensional data, like things like figuring out from an image is a multi-dimensional image what the price is less a multi-dimensional data. But like the basic idea is given enough samples and training, it can approximate any given function, any given any mathematical function. That's the idea. Like and the mechanics of that is also like we now have a very clear understanding how it is able to approximate any function and how it is able to learn anything. I call these universal approximation functions as universal learning functions, because it can learn almost anything in the world. It can learn about text, it can learn about mathematical functions, it can learn about images. So it's basically, it can learn anything. So you can either call it a universal approximation functions or universal learning functions. I have a couple of like side projects that I did which uses deep learning. I'll quickly show like an example of maybe what deep learning is capable of and what it is doing. So this is a project where I was trying to predict wildfires using satellite imagery. So wildfire is like a huge problem at least in California and definitely in many parts of the world. So I was trying to see like and the good thing is like all the wildfires here are demarcated properly after a wildfire happens. The wildfire agency here like provide a proper boundary of the wildfire. They say where it started, and they provide a perimeter, fire perimeter. So one of the problems I was thinking is like, how can we utilize this information, like this data, like where wildfires happened, and something like let's say satellite imagery, and basically predict at least 15 days in advance that a specific location is likely to have is likely to get wildfire. So here I'm basically, if you can like gather from the map, all these red dots are basically places where fire happened in a specific year, and all these like orange thing are basically the perimeters. And I'm also choosing some control points. Control point is like places, like random locations where fire did not happen. So that's also important in deep learning models, in these machine learning models, when you're training a model. And I'll explain what training is and all those things. But training means you're basically teaching the model, hey, this is a place where fire happened. And basically, let's say, yeah, this is the satellite imagery of that specific location 15 days ago, 15 days before the fire happened. So this is what I'm training the model with. 1 means like fire happened in these locations. 0 means fire did not happen in these locations. So this is a deep learning model. All I'm telling the model is, hey, look at this image. 15 days later, a fire happened in this location. 15 days later, fire did not happen in this location. So that's all I'm teaching the model. This is all that you need. Like you have a bunch of examples, you teach the model, and then like it figures out, these are all like other factors that, and basically it figures out, okay, this place, given a new image, it will be able to predict like with a certain accuracy. I can cover these accuracy metrics. This is called a confusion matrix. Like it will predict with a certain accuracy for a given image is it like a, is there a chance, is there a probability of getting a wildfire or not? So this is a simple example that I wanted to show. Like while building this model, so this was like 4 or 5 years ago. This was like a startup project I developed. I didn't know a ton about deep learning, right? I really didn't have much clue into like the inner workings of deep learning. I just knew that all I need is like, if I can figure out a way to provide get these data, get these images and the labels, I will be able to teach a deep learning model to predict me if a fire will happen or not. And it did. Like, that's at that point, it hardly took me like 10 lines of code for the actual deep learning model to train the actual deep learning model. Of course, collecting this data was another process, and I knew this due to the nature of my previous training in GIS and geospatial data. So like collecting this data is still a bit hard task. Like we still need to spend some effort on that. But once you do that, training the model itself is pretty easy. Like we have the infrastructure, the coding platforms and everything is like pretty well optimized to build something like this by yourself. And actually, I want to show you a fun example. And this was, I guess, like a few years ago. Like I guess it was this was, I guess, 7 years before, like when deep learning was just coming out. A farmer in Japan actually used it's a very trivial example, like not a breakthrough example, but like it's about how a small farmer in Japan actually was using AI to sort cucumbers, which was a task that he needed help with. He's a cucumber farmer, right? He needed help with sorting cucumbers because that's a task where he spent a lot. Like his mom spent a lot of time doing that for the big part of the day, and he was using a simple deep learning model published on a Raspberry Pi. And Raspberry Pi is a very small version of a computer, like you can get it for like 5,000 or so. It's like you can search it in Amazon, search something like Raspberry Pi, and you will find that it's a very cheap computer, and you can actually deploy a deep learning model. And when I say deep learning model, all I mean is a model which can say, yes, this belongs to this belongs to this belongs to this class, or it predicts a value. Something as simple as that. Like you saw in the previous example, given image, it will say fire or no fire. That's all it says. And it should be able to accept an input. The output is fire or no fire with a probability value, right? And so I just wanted to show this small video. It's a very trivial example, but like this, to be honest, this was an example which inspired me to get into deep learning, to learn about deep learning. Oh, okay. So if a farmer can actually learn and implement this like in a matter of days, then I too can. So that's why this video is like important for me. This is from 7 years ago. But I really wanted to share you. I hope you have this, like the 1.5 minutes. The video is long. One second, I'll start playing the video. Thank you for watching that with me. I just wanted to share that with you to show that deep learning, things like these models, machine learning and deep learning models, is pretty universal in how it can be applied. It's not like only applicable in tech or some tech domain or something like that. It can be applied in a wide variety of fields, and there is definitely a lot that everyone can do in making this much more widespread. So that example definitely inspired me, and hope it does for you too. All right, so let's going into the main meat of the presentation. The main goals that I'm trying to cover are basically at the end of the session. We should be able to identify if a ML is a good solution for a problem. Like many, there is also this view that anything can be solved by ML. Not really. ML is only good at solving a specific kind of problem, and it requires a specific data in a specific format. So one of if we are trying to be an ML practitioner, if you're trying to use ML in our day-to-day lives, we need to be good at identifying is ML even a good solution. Many times ML can solve a problem, but there might be a very simple heuristic which is as good as the ML model. And at least at Google, like, we are always told to think from first principles. If like we don't want to like trust AI and ML in everything. If something can do a job as good as ML, like with a simple a simple rule-based engine can solve your problem, then use it. Don't think about an AI or ML. Don't try to fit ML into everything. So that's the goal. And like that requires some practice, but like especially new adopters of ML. Like when someone learns ML, they start to fit everything into an ML problem. But it takes some expertise to like identify, okay, maybe this doesn't need ML. This can be solved using conventional methods. You don't need ML. So that's also an important skill for an ML practitioner, knowing when to use ML and not knowing when to use ML. And the second is, like, once you identify that ML is a good solution for a problem, how do you actually formulate it as an ML problem? An ML problem needs certain kinds of data. It requires certain kind of output. So there is some work that you need to do on that regard. So and even before that, like, how do you make sure that the ML understands what you are trying to do? You might have a goal, and it might be solvable by ML, but like it's only a specific aspect of your problem that ML can solve, right? And you need to be very clear in what you want the ML to solve. So that's the core of this thing, like framing your problem as an ML problem. And then finally, the final thing comes about how picking the right model and defining the success metrics. How do you know your model is doing a good job? So that's about, and like, how do you select, like, from a vast array of models, how do you select the right model for your specific job? And there is a very easy answer to the picking the right model. There is no right model. That's the answer. Basically, the short answer is that if you're looking for one wonder model which can solve all your ML problems, there is none. Any model which has a very which passes your success criteria. So you need to define what your success metric is. So any model which comes on the top of your which meets your success criteria is or on the top of your success criteria, that's the good model. There is no one model which fits everything. All right. So like before even going into like to identify whether ML is a good solution for a problem, like these are three stages that we go through, like to understanding the problem. And it starts with stating the goal. Like, what is the goal that you're trying to solve? And two, then once you stated your goal, determine whether the goal is best solved using ML or predictive ML, generative ML, or non-ML solution. I'll cover that, what the difference between each of that very soon. But at least like non-ML, you know what non-ML is, like the conventional solutions. Do you need ML to solve this or not? Right? And then finally, verifying that you have the data required to train your model. In the case of the wildfire thing, the data required is a satellite image. You needed two things actually. You needed the satellite images of the locations, and you needed the location where fires happen during a specific time. On which day did a fire happen in a specific area, and do we have the satellite data 15 days prior to the day the fire started? So those two are the data that's required to train that wildfire model that I showed, right? So verifying that you have the right data and the right labeling. Label, as I showed you, are those zeros and ones. Zeros means no fire, one means yes, fire happened. So these that's the data, that's the language that ML understands. So you have to formulate your data in a way that ML understands. So these are some like very small examples of like when you want to build something, like what's your defining what your ideal outcome is. Let's say you want to build a weather app. So, and this is like stating the goal in non-ML terms, right? Here at this stage, you're still not trying to assess whether ML will solve this or not, or to frame it in an ML way. Here, you're just trying to articulate in non-ML terms. So a weather app, your goal will be something like calculating precision in 6-hour increments for a region, right? So that's like predicting whether it's not like predicting comes later, but your outcome is like calculating the precipitation or rainfall data in 6-hour increments. And if you have a better way of doing it without ML, then we should go for it. But we will see like how ML can help this specific task, let's say calculating precipitation. And like let's say mail app, detecting that like we get a lot of spams, and all your mailing apps like Gmail, Outlook, and all those apps do a continuous job of identifying which mails are like spam, fake mails and things like that, and they push it to a different folder, so or delete it basically. So that's that, I would say, right, I'll go ahead and right away say that that's a ML problem, because there is no way we can define the rules of knowing which mail is a spam or not, right? Think about it. Like, let's say you as a like you want to do it manually. Like, how will you write the rules to determine whether a mail is spam or not? Let's say if it contains you define a rule like if the mail contains a specific set of words, then it's a spam. If not, it's not a spam. But then a new actor will come along and they will tweak your rules. They will if they have a good understanding of your rules that you set, they can formulate their message in such a way that it doesn't fit your rule, it doesn't pass your rules, and it can still be a spam, but you will not be detecting it. So that this is a classic ML problem, what you call as a classification problem. ML is good at this kind of stuff, like detecting spam, which a rule-based engine can't do, right? So that's a first goal, like first step, stating the goal in non-ML terms. Like at this point, we are still not telling anything about whether it's a prediction task, whether it's a generative AI task or non-ML task. We are not telling anything. We are just stating our goal. All right. So once we have the goal, we are looking at like constructing the data for oh, actually I might have skipped a slide. Maybe this is I may need to like talk about this slide before going to that. So here is a brief, very generic classification of ML systems. So very generally, you can classify all ML models into either a predictive ML model or generative ML model. And as I said, like, I'm not going to cover this because almost I feel like everyone has a very good grasp of how to use generative ML, but not much on predictive ML, right? Generative ML is anything that you can do with ChatGPT, summarizing long text, writing mail for you, generating an image, generating a video. All these are generative ML. And we are not going to cover this today. Like, I'm just going to cover the predictive ML part. So predictive ML, there are two overall, like, there are other predictive ML as well, but like very uber level, there are two major predictive ML models. One is known as a classification model, and the other is known as a regression model. That's when you're trying to predict a value. So classification is when you want to classify your input into one or two or more classes, right? So that's a class. It classifies stuff. When you like my wildfire app that I showed was a classification model. It just classifies whether a given satellite image is a wildfire prone area or not wildfire prone area, true or false. So that those are the two categories it classifies into. So that's a classification model. Or and something like whether it will rain tomorrow or not. So that's a classification model. It will the two classes being it will rain tomorrow, it will not rain tomorrow, right? And then you have the predicting value. So the housing price, predicting the housing price is a we usually also call it as a regression model, where you're basically predicting a value. So this value can be anywhere between minus infinity to plus infinity. So it's not a fixed set of values. It's like it's like a scale, wide range of scale. It can be anywhere on the number scale, but it's all it's doing. It's predicting one number, right? And all the classification model is doing is it's predicting a class, whether you belong to class A, class B, class C, or true or false. There will be fire or not fire. So something like that. So this is all the ML models are capable of doing. It will either classify your stuff or it will predict a number. So that let's be very clear on what an ML model can do. It can only do these two stuff. Very generically saying, this is all that an ML model can do, right? A predictive ML model can do. And if this fits your problem, if this is something that what your problem is trying to do, then it's probably something that an ML model can help. And the second thing is you need the data, the input data as well. Like, this is what, if your output is in this format, and two, you have the data. And when I say data, what I specifically mean is like you have historical data which has these labels, right? Like historically, like in my wildfire use case, the data is the satellite image, and I also need the labels, the classes. I explicitly need to label that this satellite image, no fire. This specific satellite image, fire. So I gave tens of thousands of such examples to train the model. So you need the input data, and this is what I call the labeling data set. So same way for housing also, housing prices also, like I need the historical housing prices. All right. So once your output is in either of these forms, and once you confirm that your data, you have historical data along with the labels, you can probably build an ML model for your problem, right? So this is very generically like identifying how a simple schema of identifying if your problem is eligible to be solved by ML or not. And once you identify this is something that you can be solved by ML, the next thing in your checklist is making sure that you have high quality input data, not just input data, but also label data, right? So there are four generic principles that we follow. One is like whether your data should be consistent, means like you should be able to collect it regularly, and or for a future instance, like that's two part. You're training your model on historical data, and then you're using your model. So once once trained, your input data is not useful. Like you just have a model, like it's a ML model or deep learning model, or you call it a mathematical model. You have the model. You need future data to predict it on. Right? Let's say you are trying to predict rain, or let's say I'll use the wildfire use case. So I need to be able to get consistent satellite image that looked very similar to my input. It should not be very different than how it looked. I should not be, even in satellite image, there are different satellites collecting different kinds of images. So their resolutions will be different. So when I'm trying to predict my output, it should be of the similar resolution. Ideally it should be from the same source, like same satellite and things like that, right? So that's the first part, like making sure that we have a consistent, reliable, and trustworthy source of input data and output data, right? And second part is like having the right labels. Label is as simple as like having historical data on what is the actual intended output, like fire or no fire. Being able to accurately identify that is very important. This is the most crucial step, getting the right labels. And many times we don't have easy way to get the labels, so we even use human evaluators. Like there is a problem, let's say something like increasingly in generative AI models, there is no way you can easily like generate these labels. So for generative AI models, like output that the kind of output that you get from ChatGPT and everything, one of the few ways that we ensure that the model is actually safe, trustworthy, and everything is actually provided by a human. Like human looks at two responses generated by the model, and a human gives a thumbs up or thumbs down, like a paid human raters, and that is about like getting or collecting the right labels. And third is like representative of the real world, means like what this means is like it simply, it should be, as I mentioned earlier, it should be representative of what you're trying to what you're trying to predict should be representative of your input. That I just want you to take that point away. Like it should not be different from what you trained on. You trained on some data, and if you're what you're trying to predict on is wildly different, your model will not work well. And the final is like having the data in the right format, like in the case of the wildfire. The small things that I ensured are like these images are like these perfect 256 by 256 pixels, and like free of cloud cover, and like in a specific image format. Like I guess it was a this image format was known as GeoTIFF or something like that. That's like format to deal with satellite imagery. So these are the data formatting issues, because like if you learn about like satellite data, the satellite data comes in a different format. Like it's basically tilted, like because the satellite moves in that manner. So there is some transformation you need to do, like to convert a tilted image into a square image. Like your actual image looks like this, but what I need for the model as input is basically something like a perfect square image. So this comes into like making sure that you have data in the right format. Right. Right. Oh, so then comes like identifying the features for better prediction. So as I mentioned earlier, you don't need to identify the features for deep learning models. For in the wildfire example, I didn't identify the features, right? But there are models, there is within predictive models, there is the two types of models. One is, as I mentioned, like the conventional machine learning models, and then there is a deep learning model. Machine learning models are models where you need to identify the feature. Let's say something like you want to predict something like whether it will rain tomorrow or not, right? Yeah, here I guess I provided weather data example. Like what you're trying to predict is whether it will rain tomorrow or not. That's what you're trying to predict. So that's an ideal case where you need to provide the features. Like you need to identify and provide the features to the model. So your features could be something like, what is the cloud coverage look like today? What is the temperature look like? What's the dew point? What's the pressure? So these are features that you can provide your model. And by features, I mean like it should also have the value. Like, what's the cloud coverage? Like 83% cloud cover. The temperature is so and so Celsius. Dew point is so and so. Like you provide values for this. And historically, hopefully you also have historical data on all these variables. And did it rain or not in the past? So given that, like in the future, you can predict, like given this data, given this data of today, I can predict whether it will rain tomorrow or not. So this slide is more about like identifying the right features. So how do we identify the right features? So there are some rules of thumb. So one rule of thumb is simply to look at higher correlation. And by correlation, what I mean is, let's say you take cloud coverage and you have your output as rainfall, whether it will rain or not. So you can simply look at past data and you can see like when it rained in the past, right? Like there are only two scenarios. It rained in the past, it did not rain in the past. The day before, what's the average cloud coverage look like? Like, was it consistently cloudy? Like what's the, let's say the average cloud cover on a rainy day, before a rainy day, is something like 80%. On a non-rainy day, let's say it's like 50%. So this is a good feature that you can use in your model, because this feature, cloud coverage, is able to inform the model something about the rain. Hey, when the cloud coverage is low, I can infer that it's not going to rain. When the cloud coverage is high, but you really don't know where to draw the line. Is it like at 60% or 70%? And there could be other factors influencing the model. So cloud coverage is not the only thing which will determine it will rain or not, but you can still determine whether it's a good feature or not, right? The ML model will do the hard work of identifying what cloud coverage is the right cloud coverage for predicting rain or not. And like with combination of all these other features, but all you need to do is like provide what is the cloud like in the past, when the cloud coverage was high, like when it rained, what was the average cloud cover like? And you see that like there is a wide difference in the average values, then it's probably a very good model, right? So you can identify for other things. There are features that, since we don't, the problem with the small problem with ML is like, since it doesn't have any restriction in what you can add as a feature. Like you can add 5 features to predict whether it will rain or not, or you can add 10,000 features, right? And one of the feature can be something like, would be like whether you can add any feature where who is in power, political power today. So which will have no bearing to the model, but you can add it as a feature. I can't stop you from adding it to your model, right? So you can add irrelevant features to your model, but it's on the ML practitioner to decide. We still have to use common sense to determine whether a feature will have any influence on the output or not, right? Something like moon phase, day of the week. Day of the week will probably have no impact on whether it's a Monday or Tuesday, will have no impact on whether it will rain or not. But you can add it as a feature. You can convert day of the week as a numerical value, and you can add it to the model, but it will have no impact on the output. And most models are good at like removing irrelevant features. It has a way of doing that, but we still have to like apply some level of cognizance, some level of common sense to identify what are the features with high predictive power and what are the features with low predictive power, right? And there are certain statistical techniques you can use to basically identify whether a feature is a good feature or not. So these are correlation metrics, and like there are certain other techniques that you can use to identify. And there is also like nothing trumps common sense, like manual exploration, identifying, having the right hypothesis goes a long way than any of these automated techniques. All right. So let's just go over a small scenario. So I'd like you to provide your answers in chat. So this is like let's say a scenario where an engineering team at a large organization is responsible for managing incoming phone calls. Means they have to decide what is the wait time look like. Like when you call a call center, customer center, let's say the company has to decide what's the wait time look like for the user, right? And so that they can inform the customer that, hey, your wait time is looks like 5 minutes from now. You will have to hold for 5 minutes. You will have to hold for 10 minutes, or you will have to hold for 1 hour. So if it is 1 hour, you can ask, probably say, hey, we'll give you a call back. So identifying this might be important for them, right? So right now, what the metric that the heuristic or the rule-based thing that they are using is, like, they are just identifying the current number of customers on hold and the number of employees answering the phone multiplied by 10 minutes. So let's say the number of current customers on hold is 100. They have 10 employees. So they say 100 by 10 is 10, 10 into 10, 10 minutes, 100 minutes. So they say, oh, you are on wait for 1.5 hours. So this is what let's say this is the current methodology that they're doing. Now the question is, would you use ML to make a better prediction? Like, you can provide your answers on chat. But the thing that I would like you to consider is, there are some customers who have their issue resolved in 2 minutes, while others can take up to 45 minutes or longer. So this is something that we know by a way of common sense. Like, we know that certain problems are solved in 2 minutes and certain. So is this a problem where you can use ML or not? All right. So I'll go ahead and show the answer. So yes. Oh, sorry. Sorry, I didn't wait too long for the answers to come in. Yeah. So so the thing is, like, this is a problem where we can use ML because the heuristic, the won't is not enough to provide a precise answer, and we can use features like number of call center phones, the user issue, what type of issue is the user having, the time to resolve, the call time, and all these things to determine what's the time on hold. So this is a problem where we can use, where we can have certain factors, use certain known factors to predict what the output will look like. All right, I'll try to wrap this up. I see that I have less time. Yeah, so finally, framing the ML problem comes to defining the ideal outcome and the model's goal, identifying the model's output, and defining the success metric. So initially we saw like what the non-ML goal look like, and like we need to like do one step to see like what's the model's goal look like. Like, let's say weather app is predicting 6-hour amounts of specific, predicting the rainfall in 6-hour intervals. Mail app predicting whether it's a spam or not spam. Like the previous example, how much time predicting what is the time on hold, right? So that's simply the model's goal. This we covered earlier. Like, most problems like is either classification problem or predicting a value, which is also known as regression problems. Yeah, finally, success metrics. This is one of my favorite topics because this is really a hard issue actually. In classification, even as simple as classification, determining whether something will happen or not, wildfire will happen or not, rain will happen or not. There are like multiple scenarios and multiple success metrics that you can actually build, or having COVID or not, right? Like COVID testing, when COVID testing kits came up, many people were talking about what's the specificity, what's the sensitivity of these testing kits, what they actually mean. And the fundamental basic of this is very simple, but like there is the nuances of this is like there are too much detail that you can derive from this very simple example, right? Like the model will predict yes or no, positive or negative, right? Or even there are multiple class scenarios as well. But let's say the simplest scenario, two class problem, it will either predict yes or it will predict no. COVID testing kit, it will predict positive or negative. Then using your test historical data, you actually know for whether the actual value is true or false, whether the actual value is positive or negative, right? So then you have these four quadrants. The first quadrant is like the model, whatever the model predicted as positive is also actually positive. So that's true positive. Then you have the false positives, which means the model is wrongly classifying something as positive. So that's something known as false positive. And then you have the false negatives. The model is wrongly classifying something as negatives, right? Which is also not desirable. And then we have the true negatives. The model is correctly predicting that it's negative. So just based on this, there are multiple metrics, other metrics that you can determine, like create to evaluate how good your model is, right? Your model can be very good at reducing the false positives, which might be your goal. Some models you might need to you prefer to reduce the false negatives. So you can think of all the scenarios where you would like to determine false negative. Think of use cases like identifying a disease. What do you want to eliminate? What do you want to reduce? Do you want to reduce false positives, or do you want to reduce false negatives? Identifying spam or not? Do you want to reduce false positive or false negative? So think of all these classification scenarios in your life and think about whether false positives or false negatives are important. And accordingly, you can choose your metrics. There are metrics like precision, recall, like specificity. You can look up all these definitions, and it's all derived from this simple matrix. But like the key question that you need to answer is which is more important, or which is more harmful? Like false positives are more harmful or false negatives are more harmful? That's the question that you need to answer when you're dealing with a classification problem. And accordingly, you can you can basically choose your model. Like based on the metric that you choose, you can say whether your model is doing a good job or not. Regression, it's much easier, kind of easier way to evaluate the model. So a common metric that we use is something known as root mean squared error, which literally, if you expand that term, error is basically your predicted outcome minus your actual outcome. For the case of housing price, let's say my model predicts 15 lakhs, your actual price is like, let's say 12 lakhs. So your error is 3 lakhs, right? And you predicted that for, let's say, 10,000 houses. So you have this error, you're squaring it, and you're taking the average of that error, and basically you're taking the square root of that average. So that's root mean squared error, right? And that value, this is a single value. Like even though you're predicted for 10,000 houses, RMSE is like one value which can convey the how good your model is, or like what's your error component on your model. Any model with a good RMSE is a low RMSE is a good model. And this metric is for regression problems, like when you're trying to predict a continuous value. And confusion matrix is for classification problems. And then, as I mentioned earlier, like GenAI is a totally different beast. There is no easy way to evaluate GenAI models because the output is not like yes or no. The output is not like a specific single number. The output is like an image. The output is like a long text. So there is no easy way to evaluate whether this is the right output or not, right? So there we have to like go into very nuanced techniques like actual human evaluation is still one of the top ways by which we determine whether a model is good, but there are also like automated ways by which we can evaluate. Let's say language translation or something like that. You have, let's say, model generative AI model is trying to translate a text into another language. So you usually use something like comparison models. Like if there is a translated text of a particular work, that will be used as a comparison, and we see how much of a match we are getting. And again, like we need not worry too much about Gen AI evaluation right now. Like, because I feel like we have already like achieved a level of democratization with Gen AI models that we have not with like the other kinds of models. All right. I will wrap up. I guess I have some. We'll have 5 minutes for questions. Any questions you can shoot in chat, or you can unmute yourself and like open to any questions that you have.
Participants, if you have any queries, you can raise.
Can we use AI in water management? Great question. So again, like we have to go through we can use, but the as I mentioned, the devil is in the details. Like, what do you mean by water management? So we need to define that. What specifically is our goal? When we say water management, what do we mean by that? And is there any specific part of the water management which is resolvable by ML? And when I say any specific part of the problem, like you can refer to this one. Like, is there any part of the problem where I need to classify something, whether I classify yes or no, whether I need to predict a value? So is this something that a part of your problem is trying to solve? And do you have historical data on all those, on what you want to classify or what you want to predict? Then yes, this is probably a use case where you can use AI in water management. So you just have to like see if a problem fits this specifically watering plants. What do you mean by watering? Whether a plant needs watering or not? Yes. If I understand your question correctly, Prashanta, right? So if the question is like you need a model to see if a plant needs watering right now or not, that's a classification problem, right? That's but the problem is the problem in that is like you need to get the historical data. You need to provide examples of, oh, this is a case scenario where the plant needs watering. This is a scenario where the plant doesn't need watering in the next 1 hour. So that you need to frame the problem and you need to provide examples. If you are able to provide that, then yes, this is a very good, very simple and something that you can implement yourself in your home even. Thank you. All right, I think we are on time. And like you can contact me on LinkedIn if you have any further questions. I'm happy to answer that. Oh, 1 second. Like there is one question. Maybe I can. One thing is, would some of like ML can be predictive, but need to be some of like ML can be predictive, but need not be exactly correct. Conditions and data is required. Yes, correct. Yeah, this is one of the things that, yeah, you're right. I guess you're making an observation that the ML outcome is not the final word. It's not, you can't, like, you have to take the outcome of an ML model with a pinch of salt, because these are probabilistic model. Again, as I mentioned in the early, when I started, like when someone says it's gonna rain tomorrow, be it anyone, be it a very good weather app, be it like the weather forecasting agency, when they say it's gonna rain tomorrow, they mean it with some level of probability, and very rarely it's 100%. They mean with a specific probability it will rain tomorrow. That's what they mean. So it's not a deterministic value. It's a probabilistic. All right, guys. I think that's my time. Thank you. It was great having you. And I'm open to questions in future also. You can connect me on LinkedIn. I will share the link of this maybe presentation in the chat. Or you can contact Professor Lavanya to reach me. That I'm open to that. Right.
Thank you, JP. Thank you for your wonderful session. It was amazing. Thank you, participants.
All right. Thanks, guys.
Is Adulia's ready, JK?
Oh, it's the same meeting?
Yeah.
Okay.
If she's ready, we'll continue with this time, or we can continue at 8 o'clock.
She might have a different laptop. Is it okay if she joins with a different laptop?
She can join with other.
1 second.